Thank you.
In this lesson, we shall focus on mathematics, applied mathematics APM 3711, numerical methods 2. Right, we shall focus on many past assessment questions in an attempt to prepare ourselves, but also to acquaint ourselves with the kinds of methods we need to learn for this module for future assessments. Right. Something that becomes very important for us is to prepare ourselves for the questions that come in the introductory part of the final paper. And now, for example, question 1, use the second order Taylor method to find y evaluated at 1.1 when y is the solution to the differential equation dy dx equals xy plus 1, and it is y at 1 equals 2. Right, let us use the second order Taylor method. Right, to actually use the second order Taylor method, we have the following. Right, first things first, we realize that what we have is actually y primed, which is dy dx. This dy dx becomes a multivariable function, a function f we call of two variables, and it becomes therefore a summation of xy plus 1, given y at 1 equals to an initial value. Now, y double primed ddx. So now we attempt, therefore, in line with the second order, we're going to find the second derivative because we want to deal with the second order. Right, so if you find the second derivative of the multivariable function fxy, so we're going to therefore have the partial derivative with respect to x and of the function f here, which is xy plus 1. Like so, with respect to x, the derivative, it's going to become what? First, we differentiate the x by the product rule, getting 1 times y, plus we keep x constant by the product rule. We find the derivative of y, and the derivative of y is y primed. We add the derivative of the number 1, being a constant, its derivative is identically 0. Okay. Now, so y at 1. So y at 1. So y at 1. Now y primed at 1, now we evaluate it because we want to determine this one here. And to determine that, we need to find y primed at 1. And therefore y primed at 1, we actually find from the y primed expression. And this y primed expression is actually exactly xy plus 1. Right, so if it is y primed at 1, it means that x is 1. Simultaneous when x is 1, y is 2. Right, so in other words, what we are saying here is the following. We have just found, because we're dealing with the second order, we have found the second derivative. Y primed. Okay, we have that. So, y primed at 1, which equals 3. Y is 2 when x is 1, and therefore y primed at 1 equals 3. Simultaneously, we want to evaluate y double primed at 1, which is y double primed is this one. And we have 1 times the y. What is the y? The y is 2. X is 1. Y primed at 1 is actually exactly a 3. 2 plus 3 becomes 5. Right, so we have got these particular constants, and therefore we're able to say the following. And therefore the Taylor in the Taylor method gives, right, so the Taylor method is going to give y evaluated at 1.1, which is approximately the same as the following. Y evaluated at 1 plus 0.1 times y primed at 1 plus 1 over 2 factorial 0.1 squared y double primed at that. Okay, I'm tempted to, this is okay, but I'm tempted to that. Let me write the general formula here. Each time they say use the Taylor, you're going to use the following formula. So the formula becomes y evaluated at x, which becomes y evaluated at a plus y prime at a 1 factorial. Then you have here, for instance, x minus a to the power 1 plus y double primed at a divided by 2 factorial x minus a to the power 2. Okay, here they said second order, so we need to stop here. But if they said third order, you're going to say y triple primed a, and then you put 3 factorial x minus a cubed. So now they said second order, so this part here we truncated, removed, like so. Okay, we write back. So that now when you want to find y evaluated at 1.1, because that's what we want, it's going to be y evaluated, because it is 1.1, what we imagine this is, so we need to first find this particular, but it is given at this value here, with this initial value. So which means that our a is 1. Normally we put an approximation. You can put an approximate symbol like this. Okay. Which is plus. Then we're going to have 0.1 over 1 factorial y primed at 1 plus you can write 1 over 2 factorial, just a rearrangement, but normally write like this, 0.1 squared y double primed evaluated at 1. Y at 1 is what? Okay, y at 1, we got it together here. Y at 1 is 2. We even have it here. Y at 1 equals 2, so you put 2 here. Plus 0.1, because 1 factorial is 1. Y primed at 1. Y primed at 1, we got it. Y primed at 1 is 3 here. y prime at 1 is 3 here, meaning we're going to put 3 there. 1 over 2. Okay, 2 factorial is 2. If you square 0.1, you get 0.01. Y double primed at 1 is 5. Y double primed at 1 is 5. Exactly like so. Meaning, therefore, why is this 0.1? Right, we have learned, therefore, that x is 1.1, but this is about 1, which means 1.1 minus 1 is 0.1. 1.1 for x minus 1 is 0.1, but it is squared. And this is called the second order Taylor polynomial. Right, so using a calculator will give us the following. Will give us 2.325. Exactly like so. And we have therefore used and solved this part of a question on what you call the second order Taylor method. You can go to third order, fourth order, fifth order, and so on. But obviously, the aim is not to go to higher order because we are time restricted. This one is a pulse assessment, and therefore we confine ourselves within the ambits of what is manageable, at least within the 2 hours of assessment time, and we move forward. There's another method we call Euler's method. On top of Taylor, there's something we call Euler's method. Now, what we call the Euler's method is used to solve a first order differential equation dy dx, which equals the multivariable function f of y and x. From x equals 0 to x equals 4. Roman figure 1. If the step length is h, and h is delta x, and this step length is 0.1, we get an error of 0.12 for y at 4. What step length should we use to reduce the error for y at 4 to 0.01? From the error of 0.12 to the error of 0.01. Okay, there are 2 possible errors, but if the step length is h, which is delta x, change in x, and it's 0.1, that is the step length. The error we get in Euler's method, all right, we get an error of 0.12 for y at 4. What step length should we use to reduce the error for 1.4 to 0.01? We investigate this question, but we answer this question very, very diligently. Now, we're going to look at the method we use to compute the error in Euler's method. Right, and we begin our analysis of this question here, but very, very carefully, as follows. For the first, Roman figure B, Roman figure 1. How do we compute the error in the case of Euler's method? But we note that, for instance, with h1 equals 0.1, okay, because we're saying h is 0.1, we are able to say we got as global error. Global error of y at 4, the value. The value E1, 0.12. With step length h equals 0.1, we got this global error of y at 4, the value E1 equals 0.12. So we ask the question, what should H2 be for us to get the global error E2 equals 0.01. That is it. And this is the plot. However, so this is sort of a question. Okay, we say with H1 equals 0.1, we got this global error of y at 4, the value error 1, which is E subscript 1, 0.12. What should H2, which is the next step size, what should the next step length be for us to get the global error E2 of 0.01? So we're saying what step length? So we need the step length H2. Right, we elaborate a little bit and say, since Euler's method is the first order method. Okay, Euler's method is always a first order method, and we shall obviously use that in solving problems. Euler's method, we shall see it. Then the global error. All right, we're just picking up on the errors that arise from the method here. Right, then the global error E, when using a step size H is given by the modulus of E, which is KH. This is the method we use. This is the formula. Since Euler's method is a first order method, then the global error E when using a step size H is given by first order method, step size H, allows us to therefore say the modulus of the error is KH for a step size H and global error E. What does this mean? Because here we have two errors. We have the area of 0.12 and the area of 0.01. So this means that the equation, right, the equation error 1, error 2, error 2 must hold. Means that the equation. This means that the equation error 1 modulus divided by error 2 must hold. Right. For the errors, must hold for the errors error 1, error 2. Error 1, error 2 when using when using two different step. Okay, we have two different step sizes, H1 and H2. Right, step sizes or step lengths. Do you want to say step sizes? They step lengths, H1 and H2. Thus, we should select. Right, we should select Right, we should select H2 as, let us make H2 the subject of this particular equation. So H2 becomes, if you cross multiply here, you can write, for example, first, let us cross multiply. If you cross multiply, you get H2 modulus of error 1 equals H1 modulus of error 2. Implies we want H2 error 2 divided by error 1. Okay. Divided by 0.12. Not 0.1. So there are two errors, the error 2, error 1, and then the H1, and therefore this is, using a calculator, is 0.0083. 0.0083. So you see, the question was, what step length should we use to reduce the error for y at 4 to 0.01? We should use the step length as obtained, 0.0083. 0.0083. Right. Okay. We continue. So the step length should be H2. So what is the formula? Is obviously the fact that the modulus of the absolute value of error 1 divided by the absolute value of error 2, which equals H1, H2. And you can see the direct proportionality of H1 of error 1 in absolute values to H1, error 2 in absolute values to H2. Next point. Next point. Euler's method is used to solve a first order differential equation. This one. From x equals 0 to x equals 4. How would this change in the step size influence? How would this change in the step size influence the local error? Euler's method, as said, is used to solve the first order differential equation. This we shall discuss the method, and we just looked at the errors at the moment that pertain Euler's method from 0 to 4. But we're asking the question for 8 marks. We're asking the question exactly for 8 marks. How would this change in the step size influence the local error? Because we have two step sizes, H1 and H2 that we've got. And to answer that particular question, we proceed as follows. We note that there's something we call the local error. The local error. in the Euler method is of the order big O of H2. This is the order, and we read the order big O of H squared. And so since the new step size is right, we know that the new step size, we have seen that we had the error of 0.12 and the error of 0.01. Right, we had the error of 0.12 and the error of 0.01. Right, and when you compute the quotient, you're getting 12. So the local error in the Euler method is of order of H squared. So since the new step size is 0.12 divided by 0.01 equals 12 times smaller, we expect the one-step error to be 12 squared. And 12 squared, we all know, is 144 times smaller. How would this change in the step size influence the local error? Because we had a change in the step size, but how will it influence what we call the local error? The local error in the Euler method is of the order big O of H squared. This is it. There's something called the local error that we compute, and we dealt with the error 1, error 2. But it is of the order big O of H squared. So since the new step size is what? Right, so the new step size we have got according to the error 1, error 2, it is therefore, if you divide the two errors, you get 12, and therefore the new step size is 12 times smaller. 12 times smaller, we expect the one-step error to be actually exactly 12 squared, which is the square of the new step. And it is therefore that we expect the one-step error to be 144 times smaller. Okay. We are yet to look at Euler's method in detail. We're yet to look at Euler's method in great detail. Still discussing what we call Euler's method, there are certain things that pertain to the method that we need to discuss at length, like being able to explain briefly why the modified Euler method is more accurate than the Euler method. The modified Euler, we're going to look at the modified Euler versus the original Euler or just the Euler method versus the modified Euler. We are yet to look at the distinction between the two, but also to use both methods to solve numerical problems. But we're saying, explain briefly why the modified Euler method is more accurate than the actual Euler method. And this becomes the elaboration on this. Euler method uses only the slope at the initial point of the interval. So we note that the Euler method uses only the slope at the initial point of the interval, whereas the modified Euler method attempts to use the slope values at the initial and final points. Okay, we're going to discuss exactly what this means. Now we're saying Euler method uses only the slope at the initial point of the interval, whereas the modified Euler attempts to use the slope values at the initial and final points. Right. We know that the Euler, okay, just mentioning this one, the Euler method is first order. Okay, we're here to discuss this method and use them in detail. And then versus the modified Euler. Right, and shall use also the modified Euler method. Okay, the modified Euler is what? The second order. The second order. In the same way that we characterized the Taylor, because this Taylor and the Euler are related. They're just related methods, and these guys just brought up these methods and they gave them different names. But now when we look at the, we're going to actually be able to see the difference. So now the second order, we're saying the Euler method is first order. The modified Euler method is second order. But this is not the kind of description that is very enough in an attempt to discuss accuracy. Accuracy of the modified Euler versus the original Euler or just the Euler method. Euler method uses only the slope at the initial point of the interval. We shall look at the examples of this. Whereas the modified Euler method attempts to use the slope values at the initial and final points. This actually encapsulates the actual fundamental distinction between the modified Euler method versus the Euler method. So we continue to solve the next question. We continue to solve the next question. And the next question is solved as follows. The next question is solved as follows. Right, the next question is how we structure our answers when it comes to questions that want us to sort of elaborate on the actual fundamental efficiencies of these particular methods. And here comes the first question. Why is a Runge-Kutta method usually preferred to a Taylor series method of the same order? Okay, so very often we prefer Runge-Kutta to a Taylor series. Why? Why is Runge-Kutta more preferable over the Taylor series method? Runge-Kutta method more preferable to a Taylor series method. One doesn't have one does not have to find the derivatives one does not have to find derivatives, because in the Taylor we saw we were finding derivatives after derivatives after derivatives. We found the first order derivative and then the second order derivative because it was second order Taylor. But in Runge-Kutta, you don't do that. In the Runge-Kutta method, you don't do that. Okay, we're going to use these methods and you're going to see what we mean, but that is actually what makes the distinction between these two particular methods. And hence, Runge-Kutta does not want us to find first order, second order, third order, fourth order, lots of the derivatives and so on. And now we're saying one does not have to find the derivatives, right, in the case of the Runge-Kutta method. One does not have to find the derivatives in the case of the Runge-Kutta method as in the Taylor series method. Right. Taylor series method. Taylor series method. Okay. Next point. Is there an upper limit to the order of a Runge-Kutta method? Justify your answer. Okay, we're going to obviously discuss the Runge-Kutta method. We've already seen the Taylor series method. But is there an upper limit to the order? Is there the highest order? Justify the answer here. Justify your answer. Right, and to answer that in short, as we elaborate on the Runge-Kutta, as much as is the highest order in the Taylor series method. So you saw that this Taylor series goes on and on and on. In particular, it runs to infinity. So in which case, you cannot describe an upper limit here. But in the case of the Taylor, but let's discuss the Runge-Kutta. Is there an order that is like the highest one? And the answer, as we said, there's no highest order in the Taylor. There's also no highest order in the Runge-Kutta. Why? And this becomes the reason why Runge-Kutta, as much as Taylor, we did the second order first in this particular past exam paper, and then now you can do more fifth order, sixth order, and so on up to infinity anyway. So even in the case of the Runge-Kutta, there's no higher order. But most importantly, this is how we respond to this particular question here. Right, this is how we respond to this particular question here. Right. We have exactly the following. No, there's something we call an nth order. An nth order Runge-Kutta. Runge-Kutta method is equivalent to an nth order right. So we're saying an nth order Runge-Kutta method is equivalent to an nth order Taylor series. Taylor series method. And the value of n can be arbitrarily large. Okay, we'll look at what that means. Can actually be arbitrarily large. in the Taylor series. In the Taylor series. Well, the short answer to this is a big no. There's no upper limit to the order, as much as there's no upper limit to the order. Yeah, by the upper limit, we mean that now with the Taylor, you saw we found the second derivative for the second order, then you find the third derivative for the third order, and then you can go high and high up to infinity. And in the case of the Runge-Kutta, no, an nth order Runge-Kutta method is equivalent to an nth order Taylor series method. And the value of n can be arbitrarily large in the Taylor series. So in the Taylor series, it can be arbitrarily large. But also in the Runge-Kutta, you're going to see the value of n can be arbitrarily large, meaning that it really can be as large as infinity, as much as it can be as large as infinity in the Taylor. So there is nothing like an upper limit to the order of what you call the Runge-Kutta method. Next question. Okay, there are some descriptions we need to give for 8 marks about the actual fundamental distinctions in the context of assessments for this module. Being in a position to explain briefly how the accuracy of a Runge-Kutta method can be determined by halving the step size at the end of each interval, or using 2 Runge-Kutta methods with different orders. Which method is more efficient and why? Okay, we obviously need to gather 8 marks in this question. And this is the past assessment question. We're trying to make sure we prepare ourselves adequately, but also we look at the kinds of questions you must be able to answer. Explain briefly how the accuracy of a Runge-Kutta method can be determined by halving the step size at the end of each interval, using 2 Runge-Kutta methods with different orders. So we get the following. We can recompute. In other words, we're looking at B Roman figure 1. In B Roman, by halving the step size at the end of each interval, we need to explain briefly how the accuracy of the method can be determined by this. And by halving the step size at the end of each interval, we can recompute. We can recompute the solution value at the end of the interval. With 2 steps of half the step length and compare the results. And compare the results. So we can, in the first Roman figure, that is B Roman figure 1 here, that's what we're dealing with. By halving the step size at the end of each interval, we can recompute the solution value at the end of the interval with 2 steps of half the step length and compare the results. And this is the reason, this sort of explains how the accuracy of a Runge-Kutta method can be determined. Because by halving the step size, we can recompute the solution value at the end of the interval with 2 steps, because you would have halved it, and we're going to see what that means. With 2 steps of half the step length and compare the results. Okay, we're going to see what that means when we solve for problems using the Runge-Kutta method. Now, there is a description you need to understand in B's second Roman figure. Using 2 Runge-Kutta methods with different orders, how the accuracy of the Runge-Kutta can be determined? If you use 2 Runge-Kutta methods, we can do the calculations using 2 different methods. We can do the calculations using 2 different methods. As an example, for an example, e.g., we can use, we're going to see this method when we get to applying them, what we call the 4th order and 5th order. And 5th order one, which is 4th order and 5th order Runge-Kutta methods. And compare the end results. And compare the end results. However, there is an observation you need to make here about the second method. Method, second Roman figure, is more efficient. Because explain, in this case, which method is more efficient. Why? So you need to explain which method is more efficient. Having the step size or using 2 Runge-Kutta methods. Okay, this is just an elaboration on these 2 methods. But now, this becomes our response to that. So method 2 is more efficient. It's more efficient by right. Also, it's more efficient since, let's put it that way. It's more efficient since by selecting the methods suitably. We can use the same K values. The same K values in both methods. And therefore, need less. And therefore need less function evaluations. Need less function evaluations. Function evaluations. Okay, let us look at this. So here we provided 2 answers to B second Roman figure when we're saying if you use 2 Runge-Kutta methods with different orders. Using 2 Runge-Kutta methods with different orders. we can do the calculations using two different methods, e.g. like, because different orders like fourth order and fifth order, but there's no highest order ones. You can say you can go to infinity with the orders of the Runge-Kutta. So we can choose fourth order and fifth order one and compare the end results. Right. So obviously we'd explain how the accuracy can be actually how the accuracy of the method can be determined. But in the second case, we're saying which method is more efficient, halving the interval or using two Runge-Kutta methods of different orders. Right. We are then saying the Roman figure 2 method Roman figure 2 is more efficient, since by selecting the methods suitably, we can use the same K values in both methods and therefore need less computation. So it is more efficient, this one, of using the Runge-Kutta methods of with different orders. Runge-Kutta methods with different orders. Right. That is something that we are actually able to take note of there. Right. Okay, we note some discursive questions. Okay, we're gonna do lots of calculations just now. Now, in view of this particular question here, right, there are certain things I would like to reinforce. There are certain things I would like to reinforce here. Okay. There are certain things I would like to reinforce in this discussion about the notion of what we call the Adams-Moulton method as we know it. To begin with, we looked at this question last time. However, I would like us to reinforce the fact that if we're required to apply the Adams-Moulton method to calculate the approximate value of y at 0.8 and y at 1.0 from the differential equation, that we're not going to spend a lot of time on this one, but I'm going to elaborate on very useful shortcut techniques. Right, the shortcut techniques follow from the fact that y primed is ty the given starting values or n1. Okay, we know that. I'm just reinforcing quickly. We shall move on to the next different question. But in actually summarizing this Runge-Kutta for this particular question, Adams-Moulton, Adams-Moulton method, we actually have, for instance, n equals 1, n equals 2, n equals 3, n equals 4. We have T1 equals 0.0. T2 is 0.2. T3 is 0.4. 0.6. 0.95. 0.68. 0.55. 0.30. 0.95. 0.88. 0.95. Okay, I know that we discussed this last time. And then 0.9. Okay, so we actually obviously are just reinforcing some facts about this, and we move forward. But would remember that we looked at this particular Adams-Moulton method last time. We looked at the two predictor corrector formulas. Now, the values of t are 0.0 we call T1, no, 0.2 we call T2, but we realize that the difference is 0.2, 0.2, 0.2 increase. So that T1 is 0.2, is 0.0, T2 is 0.2, T3 is 0.4, and T4 is 0.6. Now the Y values are the following. So Y1 is 0.95, Y2 is 0.68, Y3 is 0.55, and Y4 is 0.30. F values, T plus Y. So T plus Y, you're going to add T and Y, like you add 0.0, you get 0.95. You add 0.2, and according to the T plus Y, which is Y primed, T plus Y is Y primed. So you add 0.2 with the 0.68, you get 0.88. You add 0.4 with 0.55. Why do we add? We add because of this formula. So we just use this formula. This formula is saying addition. So we substitute into the formula, and then we're able to get what we call the F's. Why is it called F's? Because the F primed is always F of T and Y. Next. At T equals 0.8, the predictor is Y at 5 is Y4 plus. Okay, y'all would remember the predictor, but I will first write the predictor very quickly in the form that we learned. And we remember that the predictor is yn plus 1, which is yn, h over 24, 55 fn. I know we did this last time, but I'm just looking at it very quickly because I wanted to be part of our discussion today. Plus 37 fn minus 2 minus 9 fn minus 3 plus 251 out of 720. The order term, fifth order, y to the power 5 xi1. So this one is the predictor. So that y5 is y4 h over 24, 55, f4 minus 59, f3 plus 37, f2 minus 9, f1. So that you have y5 equals. Okay, why do we start from y5? We start from y5 because we already got up to 1, 2, 3, 4 y values. So now, but now we already got the y4. Remember, our y4 is the last one, which is 0.3. Plus h is the difference here, which is said is 0.2 because it's 0.2, which is, we obtained from 0.4 minus 0.2, and you get 0.2. In which case, it's going to be 0.2 divided by 24. 55. F4 is 0.9. 0.9 is F4 minus 59. F3 is 0.95. 0.95 is F3. Right. 0.95 plus 37. F2, 0.88. F2, 0.88. F1, 0.95. F1, 0.95. Right, so we're able to get y5 when we use our calculator. Right, when we entered everything last time, and it was 0.4455, we remember that. And then now we actually need to get an f5. But according to this one is f of ty, so that f5 is, this is t plus y. And t5 is the same as what? Right, so t5 is actually going to be exactly 0.8. Okay, because this is t1, t2, t3, t4, t5, which is 0.8. Okay, and then y5 is 0.4455. which means that F5 equals 1.2455. And the corrector. So this one is the predictor. So the predictor is this, remember? And then now, obviously, we're doing it that t equals 0.8. So in other words, that t equals 0.8, we're going to do two things. We're going to do the predictor and the corrector. And then now we did that last time, and we'll go quickly. We're not going to waste a lot of time there. The corrector. I want to use it today. So the corrector is, right. So first we remember the corrector formula for the Adams-Moulton. You need to learn it, but it was given this question as yn plus 1, which is plus h on 24 fn plus 1 fn minus 5 fn minus 1 plus fn minus 2 720. Okay, so you have so that you have y to the 5th power xi2. Okay, so we're getting a y5 from the corrector formula, and making n equals 4 here, and then 4 plus 1 gives us 5, so that we have y4 h of 24 here, and then we have exactly 9 fn plus 1 here is actually exactly an f5 plus 19 f4 minus 5 f we're putting f4, so this is going to be 3, and this one is going to be 2, and y4 becomes what? Right, we've got already y4, and y4 is this one, which is 0.3. 0.2 is the difference, which is h, divided by 24, 9 into f5. We have already got f5, and f5 became the preceding one, which became exactly the 1.2455. 1.2455. What is f4? 0.9. F3. Right, so F3 is 0.95. F3 became 0.95. 0.95 plus F2, 0.88. Okay. Which is 0.5037. $1.3037. So therefore, this became F5. This became F5. So the corrector is this one. Okay, so F5 therefore became this, but therefore this becomes the corrector, and therefore it is actually suggesting that y evaluated this one is approximately 0.5037, and that is associated with the y at 0.8. Obviously, we had to find the approximate values, and we did. Now, quickly, we shall remember these at t equals 1.0, until we went on to say because it's 1.8, 0.8 and 1.0, but at t equals 1.0, the predictor is what? Okay, we know the predictor and then the corrector, which is so you have this one here, Fn minus 59. Fn minus 2. Okay. So, which is 6. And then this one is going to be 0.2, that is the h, divided by 24. 55. This one is going to be exactly F5, F9, F4, 37, F3, F2. Okay. 0.5037, 0.2 divided by 24, which is 55, 1.30, 37 minus 59. F4 we've already got. We got F4 to be 0.9. And F4 came from the table, 0.9. And then we note F3. F3 is 0.95. F2 is 0.88. We take 0.95 for F3. F2 is 0.88. We actually plug them in. F3 is 0.95. F2 is 0.881. Which is 0.88. Which is 1.8856. $1.8856. And the corrector. And the corrector is Y6. Okay, we're continuing, please, with the corrector and the all right. Okay, yeah, we're going on. I'll just be with you now to continue with this. Right, the corrector, it's something we did last time. Once again, I acknowledge that, but I just need to make sure that it is part of the understanding here. So our memorandum of understanding, and therefore the corrector. Right, so, but now I'll first write the corrector formula so that you can remember it always. Yn plus 1 is the corrector. Plus h over 24 plus 19fn plus fn minus 2. So which means the corrector of y6. Making n equals 5, we did. H became 0.2 from the table. And therefore, this one is a 6. F4, F3. Y6. 0.5037. 1.8856. 1.30. 0.9. 0.95. Y6. 0.822. This is the corrector, and this means that y8 1.0, which is what we're supposed to estimate, is 0.822. We saw that using the Adams-Moulton. Okay, obviously the aim was not to spend a lot of time on the Adams-Moulton at the moment. It's something that we discussed last time. But as the business of today's discussion, I want us to move to the next point. Right. We must be in a position to discuss, like the third question, about the boundary value problem, where we are then saying consider the boundary value problem where you have the second derivative of y, and this equals y plus x. Now, y at 1 equals 1, and also y at 3 equals 2. Solve this system over the interval from 1 to 3 by using the shooting method. Use the Euler method. We're also going to use the Euler method, which we're discussing its advantages and so on, with changing x equals 1, which is the h. Right, so let us obviously use this method here in a step-by-step fashion, using what we call the shooting method. Right, so we note that in this case, the boundary value problem is given by y double primed is y plus x. Y at 1 is 1 and y at 3 is 2. So the first thing we need to do here, and I'm going to describe it in words so that you can always remember what we're doing. We must first convert the second order, because it's a second order equation. The second order differential equation into a system of two first order equations by introducing a new variable, and this new variable is going to be called z, which is y primed. This gives us the system. Gives us the system y primed, which equals z. And therefore you have z primed. So if we actually then say we let the first derivative be z, therefore the second derivative, so we're going to have this y primed here is y primed, which equals y plus x. And now you're then in a position to then say, in the place of the y prime, you put z. So that becomes z primed equals y plus x. And therefore you have y at 1 is 1. Y at 3 is 2. The question then is, what is z at 1? So we have this particular system here. And we need to solve for this system, right? Where we're then saying, what is z at 1? Because we just introduced a new variable z. So that we transformed this to from second order to a first order system. Right. So we then proceed as follows. Right. We then proceed to solve for this particular problem as follows. So now we're going to actually say, at this point, you need to let. Okay, here we'll do a couple of guesses when it comes to the shooting method. So we're like shooting, and now when we are shooting at the target. When you're shooting at a target, it's either you hit the target or you miss the target. Either you hit the target or you misfire. So now let us take the first guess. Right, let us take the first guess. Equals 0. And now we call this system 1. And solve. Let us take the system 1 and solve the system 1 with z at 1 equals guess 1 equals 0. You can see what that means. We're going to write the formula for the shooting method. But we have transformed this to first order, from second order to first order. Then now we take the first guess. We call it G1. We're going to put the G into the formula, and then we solve the system. The system 1, which we have just constructed with Z1, which equals the first guess. But it is Z1 because we are running from 1 to 3, and we are moving in stages or in steps. Now, the couple of things that remain very important here. So the calculations, right? So we note that the calculations are, okay, the calculations are y1 equals 1, okay, according to what is given. And then we're going to do z1. But you already know that, for instance, we said zx is y primed of x. That became like our substitution. So we said let this be the case. And then now we're going to compute Z1. Okay. Z at 1, which is y primed at 1. The question then is, what exactly is this? So if y at 1 is 1, then what would, for example, y prime, z at 1 is y primed at 1, right? What would y primed at 1 be? We'll see that y primed at 1 becomes actually exactly a 0, because we actually are able to see that y primed at 1 is actually exactly z at 1, but z at 1 is the first gas, G1, which equals 0, and this means that z at 1 is equal to 0. Next, we're going to compute y at 2. Remember, we're running from 1 to 3. So we're going to compute y at 2, and y at 2, to compute y at 2, you need to remember something about what we wrote here. And it is the fact that you have exactly y and the z. So, okay. Take note of the fact that y at 2 itself can be written as y at 1 plus exactly in terms of the slope, right? 1 times z at 1. Okay, in terms of the slope, so we are actually using the linear relation here. I'm going to discuss this in actually some detail just now. But if then you are actually going to do the y at 2, right, and this y at 2 would therefore be given by exactly the following. Okay, we're going to write that one down. I'm looking at the best way to explain this. But you're going to see that your y at 2 is y at 1 plus 1 times z at 1. So this corresponds to actually the slope. And then if you look at the slope, because you actually have been able to obtain a couple of computations. Y at 1 is 1. Right, so if y at 1 is 1, but also we know that y primed at z becomes y primed at x, is actually equal to z. Right, and also we actually have been able to see that if y primed is z, this gives us z primed is y plus x. Now, if we use these relations here, we're able to see that if you compute, for instance, an average or the actual difference between y2, because this is 1 up to 3, so you have 1, 2, 3, for example, in steps, the interval 1 up to 3. So we did y1 z1, so we're going to do y2 z2. Now, if you do y2, then we're able to see that, in essence, what this becomes is y2 minus y1, or you can say y2 equals y1, which is equal to, right, the slope times z at 1. What is y at 1? Y at 1 becomes exactly a 1 plus 1 times. What is z at 1? We said z at 1 is 0 because it's the initial gas. Right, so you can put exactly a 0 there. Right, I'm sure you will get a sense of what we're doing here. And then now this is actually exactly the same as 1 plus 0, which is exactly a 1. So we got y at 2, but we need to find z at 2. Like we get y, z, y, z. Y at 1, z at 1, and then we get z at 2. Z at 2, if you get z at 2, then you must say z at 1, because see, the idea is This is like change in y. Change in y. So if you're doing changing, like this is going to be change in z. So it's z2 minus z1. And then 1 times. At this point now, this is going to be associated with what? It's going to be associated with exactly the following. So this one is going to be associated with, for instance, the z primed. Right, so if it's associated with z primed, we saw that z primed is equal to y plus x. Okay, this is z, y primed primed. And then we got this from the previous system, z primed equals y plus x. So you'd come here and then put the y plus x, which is z primed. So which is y1 plus 1, which is z at 1 is 0. Y at 1 is 1 plus 1. So here, what did we put here? Here we have used z primed here. And here we just used z. But here we used z primed. And so now, and then this is what we are getting exactly. So it is that, but when you add everything here, it becomes 2. Then there is y at 3. There is y at 3. So y at 3 is equal to what? According to this, y at 3 is going to be y at 3 minus the previous one, y2. Okay, because if it's y2, then it's 1 less. 2, 1. So if it's y3, then it's y2, 1 less. Plus. And therefore, now we're going to use the following because at this point, we actually used the fact that this y1 was y1, and then we used z1. And this was y2, and then obviously we went on to actually use our z primed there. And then now, the next thing we're going to use is that we're going to use 1 times z2. Because it's 2, 2. 1, 1, 1, 1. So you can see it's y1, z1. And obviously at this point we use the z primed there. For the z, we use z primed. But for the y, we use z's. Whereas for z, we use the z primed. For y3, we're going to use just z. Right. So remember that obvious associated with our delta x. Our delta x, that is actually 1, and hence the 1 we are putting here. The delta x is 1, and hence the 1 we are putting right through there. But also the fact that the delta x is 1 means that we are moving from 1, you add 1, get 2, add 1, you get 3. So, okay, what is y at 2? Right, so actually, obviously, we can be in a position to get exactly y at 2. How can we obtain y at 2? Right, how can you obtain y at 2? Right, so it is easy, and we shall discuss this, the fact that y at 2 itself can actually be seen as exactly a 1. But what is z at 2? Right, the delta x is 1, giving us 1, and then z at 2 would be given as exactly a 2. And 1 plus 2 would give us exactly a 3. Okay, let us reason this out methodically. Let us reason this out methodically. Remember that z at 1 was seen as the equal to G1, the first gas, because we're starting at 1. That is why the first gas was Z at 1. And therefore, but we know that each time we want to find Z, we use the equation Z equals Y primed. But this means Y primed at X is Z at X. Okay. Simultaneously, we already know some of the equations, like Z primed at X is Y plus X. Right, so, but obviously simultaneously, one can look at this as Z primed at X and Y to actually be the same as Y plus X. Now, if this is the case, you can be in a position to use this, as we said already. We got Z at 1, like we got Z at 1, which was 0 according to the initial gas, and it was Y primed at 1. So if Y primed at 1 is Z at 1, and Z at 1 is 0. So this, for instance, gave us the value of Y primed at 1. So now, there are certain things then that you need to take note of here in computation with our Z2. Using Z2 equals this, so we're able to see that Z2 is equal to 2. And obviously we came here and we put Z2 equals 2, but we use the fact that we know Z1, and then we know also for the Z, this one we used Z primed, and we got the Y3 at 3 because Z2 is 2, using the fact that the delta X is 1, but to find Z2, you need to use Z1, delta X, which is 1, and then we put Z primed there. And in other words, whatever you say, you can actually be in a position to be rest assured that here in the Z's, we're using Z primed, in the Y's, we're using just that. Okay, yeah, we're going to discuss this a bit more at length. We'll move on to the next point. Now, we actually will continue to analyze this with so much caution. Right. So this observation, we got that Y3 is 3. What is the meaning of this? Y3 is 3. So the value obtained for Y3 was R1 equals 3. You see, the value obtained for Y3 was 3, and therefore we call it the R1 value in view of the shooting method. So it was R1 equals 3. But this R1 equals 3, we note that which is not equal. Is not equal to the required value. Is not equal to the required value. D equals 2. Is not equal to the required value. D equals 2. Right, so it's not equal to the required value, D equals 2, because this is the value. So now we got Y3 is 3, but we expect Y3 to be 2. So we misfired. We misfired because we are shooting. Either we shoot and hit the target or you misfire. So here we know that Y3 is 2, but we got Y3 is 3. So it is a misfire. So we missed the target. So the value obtained for Y3 was R1 equals 3, which is not equal to the required value D equals 2, this one. Okay, let's continue. So let us make another guess now. Therefore, we must make another guess. Let us take guess 2 to be -1. We took the first guess to be 0, right? Right, so we have this. We said let us take the first guess to be G1, guess 1 equals 0, and solve the system with this, where guess 1 is Z1. Now, therefore, we must make another guess because that guess was not good. We misfired. We must take another guess. Let us take guess 2 equals -1. With this one, let's see what we're going to get. But it is done with Z1 equals guess 2. So we start from the beginning, because it's 1 to 3. So we start from Z1, which equals guess 2, which is -1. The calculations are the calculations are okay, continue, please. We continue. Let's start with the calculations like we did. So if the first guess is, okay, so we're going to need to write a couple of steps here. Right, we're saying the first guess is Z of 1, which is our second guess. We call guess 2 equals -1. It's just a guess. We take the values that are smaller than this, the 1. And therefore, we took first 0, and then now we're taking -1. Because we're looking at the interval from 1 to 3. So if you look at the number line 1, 2, 3, and then we are looking at these here. So you need to take numbers that are smaller. So we took 0 on the number line, and then now we're taking -1, and then we try and see if we can hit the target. Let us see now. Right, so Z of 1 with the Z of 1 equals guess 2 equals -1. Calculations the calculations are y at 1. Okay, we start. Okay, we forget everything we've done. Okay, because that case was not good enough. All right, so y at 1 is 1. We start again. Then we're gonna do z at 1, but we remember that we said let z be equal to y primed. If z is equal to y primed, then it means that we have this, but also this one, it means that wherever there's y primed, then it means z primed is y plus x. Y plus x. So Okay. Z at 1 is the same as -1, according to this. Z at 1 is -1, according to our gas. So it's our gas. And then now we're going to do Y at 2. We remember that Y at 2 must be Y at 1, and then there must be some delta X multiplied by Z at 1. So that is the formula. So Y at 1, it's a 1. Delta X is 1. Z at 1 is -1, giving us 0. Then we found Y1, Z1. Then we find Z2. Z2, the formula for Z2 is going to be Z1 delta X. And then we saw that we going to do, this is Y1, Z1. So, but with the Z here, we're going to use Z primed. Z primed at 1, we saw that. So that Z at 1 is what? Z at 1 is actually exactly -1. Delta X is 1. Z primed at 1 is this one, is Y at 1, and Y at 1 is 1. And then X is 1 because it's Y at 1 and therefore X is 1. Y at 1 means this is Y at X. So Y at 1, it means X is 1. And therefore this means 2 minus 1 is exactly a 1. So that then we have the following. So now we need to get a Y at 3. Right. So when we get this Y at 3, what is happening here? So Y at 3, according to what we have done, according to this, is Y at 2, because Y at 2 is Y at 1. And then you add the things here. But Y at 3 now, we go back to the Y, but it's going to be Y at 1 less, Y at 2, delta X. Right. Okay, good. Let's continue, which is delta X. Okay. Then you have this one is going to be exactly Z2 because you've already got Z2. So which means that Y2, we've already got already Y2. And right, in particular, let's see what we've got. Right. So you have Y2 is 0. The delta X is 1, Z2 is 1. And the answer is 1. So we comment upon this answer we've got. So we note that here we obtained a value R2. It was R1 before. A value R2 equals 1. Now we got 1 for Y3. Still, we did not get, we're supposed to get 2. Right. But again, it is not equal to D equals 2. We need 2 for Y3, we need 2, but we got that Y3 is 1, so we still misfired, and therefore we need another gas. We need another gas. Okay, let's continue now. We guess again. And we note that this is very important because we misfire 2 times. So when we misfire 2 times, it gives us a lesson for the problem. This time, since we have, this is a shooting method we're using. This time we have available. We have available. We have available for us. We have available for us the results. The results of 2 guesses. Right, the results of 2 guesses. We use the technique of interpolation. Of interpolation to make a better guess. To make a better guess. The interpolation formula. So when we have 2 guesses, then we use interpolation to make a better guess. Now let us see how interpolation is going to help us. So the interpolation, the interpolation formula is, right, so the interpolation formula is going to be guess number 3 minus guess number 1 divided by the D we want, which is 2, minus the R1, which was the first result we got. Guess 2 minus guess 1 divided by R2 minus R1. Where guess 3 is the next. Is the next. Is the next guess. We therefore get the G3 is the next guess because we have done like 2 guesses now. So we use this interpolation formula when we guess 2 times and we misfire. And then now we're going to actually be able to get the third guess. And the third guess, if you look at algebra, you cross multiply and make G3 the subject. So guess 3 would be guess 1 plus guess 2 minus guess 1 divided by result 2, result 1 we've got. D, which is 2 minus R1, which became result 1. Now we are in business. So the value of the next gas. The value of the next gas is guess 3 is equal to, we saw the interpolation formula, so it's guess 3 plus guess 2 minus guess 1. And then it is D minus R1. So now, what is guess 2? Guess 2 became minus 1 and guess 1 was 0. We guessed minus 1 and then guess 1 was 0. R2 became 1 and then R1 we got 3. So you can still remember that. And then the D is this one. So the D is 2, but R1 became 3. If you simplify everything here, this one is exactly a -2, and this becomes a half, and then this is minus, so it's minus 0.5. With Z1. So with Z1 equals case 3, and now our case 3 is minus 0.5. So we use the interpolation formula. So now, would say with Z1, now we have used the interpolation to find a beta gas. We hope to hit the target with the interpolation formula. So with Z1 equals gas 3, you always go back and start from the beginning at 1. Gas 3, which is minus 0.5. The calculations are y at 1 is 1. Y at 1 is 1. Okay, because y at 1 is 1 here. And then we find, as usual, our Z. Substitution. Z at 1, because it's our case 3, which is minus 0.5. After that, we're moving from x1 to 3. So 1, 2, 3 are the steps. So now we're going to go to y2. What is y2? We saw that the formula would be y1 and then delta x. Delta x is 1. And then we multiply it by z1 at 1. And then y1 is 1. And then delta x is 1. And the z1 is minus 0.5. And the result is 0.5. Z2. Z2 is Z1, and then we're going to do delta X, and then we're going to do Z primed at 1. So, what is Z at 1? Okay, Z at 1, we already know is minus 0.5. The delta X, it's a 1. Z primed at 1. What is Z primed at 1? Okay, obviously for that one, would remember that in the beginning, we said to change this one from second order to first order, we said let Z be y primed so that Z primed is y plus x. So what is Z primed? Z1 prime is going to be y plus x. At 1, y at 1 is 1, but the x is what? The x is also 1. Right, y is 1 and the x is also 1, and therefore this is 2 minus 0.5, which is 1.5. So now then we have y at 3. Okay, this because now we did y1, z1, y2, y2, z2, then we do y3, then we can do obviously then we want to see the y. So what is y3? We saw that y3, the formula for y3 is always y2 because it's 1 less delta x, and then for the y becomes z2 because y1, z1. What is y2? Y2 we already know is 0.5. The delta x is 1. Z2 is 1.5. And then 1.5 plus 0.5 gives us a 2. Voila, we got the answer. So now we have hit the target. Because through the interpolation formula, we misfired twice, but we have hit the target. Right, so, and we note that we see that the third gas, leads to the correct value of Y3. It leads to the correct value of Y3, which is Y3 equals 2. Right. And our conclusion, therefore, is the following. Right. The conclusion is therefore the following. The approximate solution to the boundary value problem is therefore so the approximate solution to the boundary value problem is therefore what? Is therefore that y at 1 is 1, y at 2 is 0.5. We've seen that. Y at 2 is 0.5. Y at 3 equals 2. Right, so this therefore is the shooting method, the method that we so much need to understand. And I'm sure that we have gone through this, but also we, as a matter of fact, tried to make sense of what needs to be done. We can recap with this, but also we shall look at other problems that involve the shooting method. Okay. And also the shooting method goes hand in hand with the with what we call the interpolation formula. So now this interpolation formula we have here, interpolation formula is the formula that is very important. But this formula allows us to say, if you make two guesses where you miss 5, you can always expect that, you can then use this interpolation formula to find the third guess. You made guess 1, guess 2. So the formula therefore says guess 3 minus guess 1 divided by the D, which is the actual result, minus result 1, which we got is the value of Y3. And then now we say guess 3 minus guess 1, guess 2 minus guess 1, and then R2 minus R1. Okay. Next. Question 3. Now, in question 3, compare briefly the shooting method and the method of finite differences. Okay, it's very important that we're able to understand the shooting method we've just discussed and the method of finite differences in solving boundary value problems by stating the main advantages and the main disadvantages of each method. Right, so let us compare these, the shooting versus the method of finite differences, but also you have both advantages and also disadvantages. First, we look at the shooting method. After the shooting method, we're going to look at the method of what we call finite differences. Right, the method of finite differences. Finite differences method. Right. Okay, let's look at the plus. So that's certain to give a solution even in the nonlinear case. Okay, these are advantages and then there are disadvantages. The advantage of the shooting method is that it's certain to give a solution even in the nonlinear case. If in the nonlinear case, it can give you a solution. But this one, the downside of it, or the disadvantage of it, is that it requires more computational effort, like you've seen. It requires more computational effort. The method of finite differences, we're yet to discuss problems that involve the finite difference method, but it requires less computational effort. It requires less computational effort. The method of finite differences requires less computational effort, especially for higher order systems. For higher order systems. Higher order systems. And then we go on to say, may not converge. The downside of the finite difference method is that sometimes it does not converge. So may not converge if the equation, especially if the equation is non-linear. So you have an equation that is not linear, especially if the equation is non-linear, and the initial estimate is not good. If the initial estimate is not good, the method of finite differences may not converge, especially if the equation is nonlinear and the initial estimate is not good. So you might start with an equation that is not linear that you need to solve, but using the method of finite differences, and the initial estimate is not good. If the initial estimate is not good, then the method of finite differences may not converge. Simultaneously, it is less computational. It may not converge, therefore, is the downside of the finite difference method. The downside of the shooting method is that it requires more computational effort. But now the upper side is the advantage, less computational effort, especially for higher order systems. The shooting method is certain to give a solution. The shooting method will surely give you a solution, even in the non-linear case. And that is like the upside of it. So yeah, we have discussed this, and I can see that we have actually reached our cut-off time for today. And we actually will continue tomorrow. And in our discussion tomorrow, we shall look at more methods that we need to learn in this case. That will help us understand how to tackle problems in this area. All right, and we have more problems that require Runge-Kutta, the method of finite differences, and other methods that we need to master as we learn the course. Right, any question?
No, I understand. I'll just go over the recording again just to freshen up before tomorrow.
Good,
But
good.
so far, I understand.
Okay, good. I'm glad that at least you can make sense of the things. We shall continue looking at other methods tomorrow. Okay, but thanks for joining us today. It was awesome having this discussion. We shall send the recording in the next couple of minutes. Until tomorrow, take care and goodbye.
Thank you. Bye.
Thanks. Goodbye.